welcome again. I'm Teresa Sicignano, a PhD student from Naples, and actually I'm doing my studentship at ISO Garching. I will talk about how to measure astronomical distances with Cepheid variables. So let's start from this plot. And I will go to focus on the first step of the extragalactic distance scale, that are the period luminosity relation of classical Cepheids. And we already know that this first step is important and crucial because we'll go and will serve to calibrate the supernova 1A distances and then to measure the each zero. So every error that we do in this first step will propagate up to the measurement of each zero, and it's very important to take into account every possible systematics that can appear. So the first thing that I want to show you is the first plot of a period luminosity relation that was presented more than 100 years ago from Miss Henrietta Leavitt. And you can see here that she observed the classical Cepheid in the small Magellanic clouds, and she, thanks to a logarithmic plane, she found out and she noticed a relation between the period and the luminosity, the apparent luminosity of this object. And so she also suggested that probably this relation was only linked and the period was only linked to the mass density and to the surface brightness of this object. This means that was an intrinsic property of the star. Indeed, here we can see just, for instance, that I will talk a lot about SMC and LMC. These are the two most close galaxies to the Milky Way, and they're dwarf galaxies that are interacting both together and with the Milky Way. Indeed, Miss Leavitt was working as an Harvard computer, and we can see here a photographic plate and how she named the star. And her role in the Harvard Observatory was only to catalog the magnitude of the star that she was finding in the different plates. And she was, her intuition was very important because she found out that, first of all, some stars, these are the light curves of the time series light curve of Cepheids, and we will show later also the shape. She found out that these stars were periodic. This means that there was the same time passing between the maximum or the minimum of this star. Indeed, as we can see here, these are the light curve that Miss Henrietta Leavitt proposed in 100 ago, and these are the re-observed light curve of this star. And we can see that more or less the shape is the same as we anticipated this morning. The problem at that time was on the minimum, that indeed is the maximum of the magnitude, and this was because of crowding, of reddening, because at that time there were not so much instruments to analyze this. But we will go later in detail about this. So this talk will be very complementary to the one that Louise had. Indeed, as astronomers found out this relation and that this relation could be used to measure distances, they understood the power of this relation. Indeed, thanks to this, Hubble was able to state that there were not only the universe was not only the Milky Way, but indeed all the other galaxies that they were observing were outside the Milky Way. Because indeed, as you can read in the paper by Hubble, they stated that they were observing some Cepheids in the direction of Andromeda galaxy. They still did not know that the Cepheids were in Andromeda galaxies, and they tried to search for a distance thanks to the period luminosity relation. Indeed, at that time, the calibration was different because they only could have parallaxes of some small object, and they were used to calibrate the light curve in a different way that today we are no longer using. But still, they found out that Andromeda was outside of our galaxy. And also here, Hubble, in a public conference in Washington, state that this tool was powerful, and still he wrote that while astronomers are not clear as to the causes of this remarkable relationship between luminosity and period variation, they believe that it holds good for all Cepheid variables. And indeed, this was the cause of the error on the estimate of which 0 is stated good for all Cepheid variables. But first of all, I want to focus on this first point. Astronomers are not clear as the causes. So this motivated another astronomer in the last century, that is Sandage, to think about this relation. And indeed, he was observing the period luminosity relation of classical Cepheids both in M31 and in M33. And he noticed that while the slope was more or less the same, the dispersion of the relation was not the same. And he supposed that this was not only because of magnitude errors, of accidental errors of measurement, but that there was a third parameter. That was the color, because we know, for color in astrophysics, we mean the difference between two different magnitude in two different filters. And he supposed that we don't have to talk about the period luminosity relation, but instead we have to talk about the period luminosity color relation. And why this is possible? Let's go to the physics. So we are saying that a Cepheid is a pulsating star. So we can link the period of the Cepheid to its density. And also we know that all the stars are black body, so they are irradiating as black body. And from the Stefan Boltzmann law, we can take the relation between luminosity, radius, and effective temperature. But now, why a Cepheid is pulsating? We have to imagine that the stars are made of different layers, and in the external layer, by some kind of statistical effect, the opacity can increase, and this opacity will cause a surplus of energy. Indeed, the two mechanisms at the basis of the pulsation are the kappa mechanism, that say that the opacity in the external layer of the star is increasing, and the gamma mechanism, that say how that surplus of energy has been collected inside the external layer of the star. Indeed, in the external layer of the star, what causes this opacity is the helium that is presented both single or double ionized. So this means that there are different atoms, and this presence of different quality of helium will cause also different pulsation. For this reason, we can say that a Cepheid is pulsating first overtone or fundamental mode, because this is as you have to imagine playing an instrument. Sometimes you have only one note to create a note. Sometimes you have to create two notes to create a different note. So this means that you can have a single wave or a double wave. And this is what can happen in the external layer. So what happens for a Cepheid is that during contraction phase is taking more energy, is storing more energy during compression, and this more energy will be released during expansion. And for this reason, we don't have a linear magnitude, but we have less magnitude, and this is the minimum of the light curve, less magnitude when we observe during compression, and then we have more magnitude when we observe during expansion. And we can say that a pulsating star is behaving like an engine, a heat engine that is storing energy. And the important point to have in mind is that the only things that causes pulsation are the small change in opacity in the external layer of the atmosphere. So, if we want just to say some numbers formula, first of all, the first thing that we are always to take into account is that the star is a self-gravitating sphere that is going under pulsation. And we have also to take into account that the variation of the radius during pulsation are small, so we can still talk and think about one radius that will describe all the stars. Then we have to think about the pulsation as a pressure perturbation, and we can say that's moving with the speed, with the velocity, the speed of the sound. And at this point, we can have a relation between the period of pulsation and the mass and the radius. Then we can take from the Stefan-Boltzmann law the relation between the radius and the luminosity and the temperature. And an important point to remember now that we still don't have talked about this is that the two main things that determines the life of a star when the star starts the path into color magnitude diagram are its mass and its chemical composition, because these two will say how the mass or how the star will evolve during evolution. And we will say also later how the chemical composition will enter in this relation. So at this time, we can see that the period is a function of the mass, of the luminosity, and of the effective temperature. So, and then, since we as astronomers want to work with linear relation and with linear coefficient, we just take the logarithm of this so that the exponential can go down as a coefficient. And so we have a relation between the log of the period, the luminosity, the mass, and the temperature. Indeed, for pulsating variable star, mass and luminosity, they are linked, because as we will see later, mass is the important key that say to the star when it can start to pulsate. And so we can remove these, since the mass is not independent, we can take these together with the luminosity. And in the end, what we have now, that the period is dependent on the luminosity and on the effective temperature. So we have one function, the period, that is depending on two other variables, the luminosity and the temperature. This means that we can create a plane to observe this relation. And this is the period luminosity color plane. Indeed, here on the 3 projection, we can see all the physics that we need to know about pulsating stars. Why? Because, as you can see here, the projection of the period luminosity color plane on the plane only of period and luminosity is the period luminosity relation. Then, the projection of the period luminosity color plane on the axis of period and temperature is the period color relation. And indeed, the projection of the period luminosity color plane on the log L, log T is the color magnitude diagram. And we will see later what happens when we do this different projection. Indeed, what we can say now is that, first of all, what I wanted to say, is that if we are talking about observable quantity, because we don't observe like the luminosity, the pure luminosity, but what we observe is the magnitude, and what we observe as temperature is a color. So if we want to talk about observable quantities, we have to change our definition, and indeed, what we use in the extragalactic distance scale is this version of the relation, where we see that the magnitude, the absolute magnitude of the Cepheids is given by a coefficient for the period plus a delta for the color. And here you can also see that is missing the gamma term, and you will see later where the gamma term will enter in this relation. So, at this point, what we can notice is that, first of all, the period luminosity color relation is a relation that holds for each individual Cepheids. This means that every time that we know the period and the color, we can retrieve the absolute magnitude of that Cepheid, and we can retrieve also the distance. But why we don't use the period luminosity color relation in the extragalactic distance scale is because the color is causing more systematics and is just entering with some problem. For this reason, we prefer to use first the period luminosity relation and later I will introduce another relation. But the problem of the period luminosity relation is that the period luminosity is a projection of this plane on the period luminosity plane. This means that is a statistics relation, and we need to populate this plane in order to have the better condition to have the better period luminosity relation, because also if you remember, as Luis showed this morning, we want to populate as much as possible the period luminosity relation, and because at that point we can know the perfect alpha, that is the 0 point that is at the core of our problem, because we want to know this 0 point that is the distance in magnitude modulus and the slope of this relation. And as much as we populate the strip, we can say, okay, I'm pretty confident with my results. And for this period luminosity relation that we have seen that is based on physics, and so, I mean, we know the physics that's behind the pulsation, we can see that Cepheids are standard candle. So now, let's talk about the projection of this period luminosity color plane on the color magnitude diagram, because this projection just cause the instability strip, is what we call the classic instability strip. Because as soon as we observe a color magnitude diagram of some galaxies, and we know that stars are in this region, we can say that these are radial pulsators. So this means that for this star, there is a period luminosity color relation, and that we can obtain the magnitude from this relation. So the first thing that I want to say is that stars can cross this path in different time of their evolution, also more than once. For instance, classical Cepheids can just cross this strip for 3 times. And then what is the fact that the strip is just as a blue edge and a red edge is what caused pulsation. Then, pulsating stars, variable stars, why they are important? Because thanks to only the observation of their light curve, we can have not only the magnitude, but we can obtain also the period and the amplitude, that they tell us something more about the physics that is inside the star. But now, let's see what are the stars that populate this instability strip. First of all, we have the classical Cepheids. Classical Cepheids are young stars, and we say that, so this means that they are population 1 star. We will see population 1 star. When we say population 1, we mean that the stars are young. They can have masses between 3 and 13 solar masses. And for this reason, I mean, they are young, so they have higher masses than the Sun. And they can pulsate between 0 and 100 days. And this means that when they have a small period, they will enter the instability strip in the lowest part. Indeed, when they are highest period, they are more luminous, and they will enter the instability strip in the highest part. And they can pulsate in fundamental first and sometimes also in second overtone modes. And this is because the external layer of the star can have different kind of opacity, and this will cause more modes in the atmosphere. So another class of pulsating star that has been used in the past centuries, only 1 century, are the RR line, because they are population 2 distance indicators. This means that they are old, and as we have seen this morning, Cepheids that are young, they can suffer of crowding because sometimes they are found inside the galaxies, not in the outskirts of the galaxies. Indeed, RR Lyrae can be found in the outskirts, and they will suffer less of reddening and of extinction and of crowding. And they are being used to trace the population and the distances in the local group. But indeed, since as you can also see here, they are not so luminous as the classical Cepheids, they cannot be used to go beyond where there are also supernova 1A. But still, they can be useful tracer in the local group to search for systematics. Now, let's talk about type 2 Cepheids. Type 2 Cepheids, they are also population 2 distance indicators. This means that they can be found not only in elliptical galaxies, but in different, all the kind of galaxies. Moreover, they are crossing the instability strip at a different evolutionary phases. Indeed, classical Cepheids, they are crossing during the horizontal branch, and they are a core helium burning. Whereas BL Hercules are moving from the horizontal branch towards the asymptotic giant branch. They are post-horizontal branch, so this means that they are almost finishing to burning helium in the center, whereas BL Hercules are these in the lower part. Then we have WVIR, and you can see that WVIR still entered the instability strip after BL Hercules. This means that they are after the asymptotic giant branch phase, and since they have evolved shell, they can have also instability, thermic instability in the outskirt of region. And then there is also a third class that, for historical reason, is associated with the type 2 Cepheids that are Arvu Tauri, and these are more complicated. For this reason, they are not used in study of distance ladder or similar, because they are evolving toward the white dwarf phases, and the external layer of the atmosphere is so chaotic that this not allow us to say, okay, this magnitude is related to this star and we can use this as distance indicators. But still, they are pulsating. The core is pulsating in a radial way, but since the atmosphere is going through instability, they are not trustable as distance indicators. So, indeed, just because we will see also at the end of my talk that these Cepheids are not used only as distance indicators, but also as population tracers, we can say that RR Lyrae and type 2 Cepheids trace a different population with respect to the classical Cepheids, and indeed they also have different, if we look at their proper motion, they trace different evolutionary paths. Indeed, the last class that I want to present you is a funny class that's called anomalous Cepheids. Why? Because in the last century, the first time that they were observing these stars, they found them strange, because they were not bright as RR Lyrae. They were more bright than as RR Lyrae, but still less than classical Cepheid. So they say, okay, let's call them anomalous Cepheids. And they were, for the first time, observed in dwarf galaxies. And still, as you can see here, also in the instability strip, they are placed between the population 2 and population 1 distance indicators. So they are intermediate age and also intermediate mass. And the fact is that they are really metal poor, according to recent studies, and it's still not clear at which time of their evolution they enter the instability strip, and if they come from binary or single evolution. But still, we can say that all of these that I show here, they can be used as distance indicators, but differently from what was taught in the last century, they do not follow the same period luminosity relation, but they follow different period luminosity relation. So in order to use them as distance indicators, we have to choose a star, a pulsating variable star, and we have to use that type on all the distance ladder to obtain the right distance. Indeed, here in this plot, you can see the period luminosity relation of the stars that I presented in the Large Magellanic Clouds, because we prefer, to plot the Cepheids in the Large Magellanic Cloud because this galaxy is far from us, but not only this, its position is face on with us. So we can know that all the stars that we observe, they are at the same distance from us. And so in this case, we don't need to do any correction or anything. We can just observe the star. This is an observed magnitude, and we can retrieve different period luminosity relation. Indeed, later we will see that these, you can also already see here the absolute, this is not the absolute, this is the apparent magnitude of this relation is around 18. But here we don't have any correction or any calibration of the 0 point. And you will see that only with a small correction we can obtain the distance of LMC, because on this axis we don't only have the magnitude in the K-band, but this is also an axis of the distance modulus in magnitude, because we are used to say that distance in astronomy are measured with parsec, with redshift, but also with magnitude, because especially for standard candles, if we know the magnitude at a given point, then later what we observe is another magnitude, and we can compare these two magnitudes, and we can obtain a distance that is a distance modulus. But at the end of last century, there were, after all this discussion, there were still some limitation of this period luminosity relation. For this reason, to go into the 1% precision that Luis showed this morning, they had to investigate every source of dispersion and systematics. And the three major points that give systematics to the period luminosity relation are, first of all, the width of the period luminosity relation, because if you remember, is a projection of the period luminosity color plane. Second, the extinction. Why? Because the light that we observe, that we collect at the telescope, is not the light that was produced by the star. It has to go through the universe to arrive to us. And then the metallicity, because as I've told you, the metallicity play a role into when the star crossed the instability strip. And so can happen that stars with the same luminosity, they have different metallicity, and this impacts the distance measurement. First of all, let's say the width of the period luminosity relation. Here you can see an example of the Cepheids populating the period luminosity color relation, and you can see that changing the projection angle will change the width of this relation. And the things that we want to do is to have the small dispersion, because if you project the relation in a different angle, you will have more dispersion. And this is links to the fact that period luminosity relation has a finite width that's given from the period luminosity color plane. And so we need to populate it better with more and more points. Then, the second problem was extinction, because as I told you, the stellar light that comes is absorbed and scattered by the dust and by the gas during the travel into the interstellar medium. And this effect is called interstellar extinction. And the extinction reduces the luminosity, the magnitude of the star that we are observed. And also alter the colors that, as I've told you, the colors is a proxy for the temperature. So what happened is that we have to take into account this, because we have to take into account the travel of the light that's coming. This means that when we observe a magnitude at the telescope, we have to correct for the extinction, and the extinction changes in every photometric band. Moreover, you can say that the extinction follows this relation where R is the law, the extinction law, and the extinction law is linked to the size of the dust and of grains in the direction which we are observing. Then we have also to multiply the extinction law for the extinction itself, that is measured in other independent way, observing the dust and doing maps of the Milky Way. Indeed, as you can see here, the extinction is not behaving the same in all the photometric band. Indeed, the extinction is impacting more our measurement in the optical. For this reason, I've shown you before the light curve of Miss Henrietta Leavitt that were observed in the optical band were suffering more from the extinction, because also imaging that that measurement were taken by hand by Miss Henrietta Leavitt from the photographic plate. But nowadays we have more instrument, and also for this reason, for the shape of this curve is why we observe in the infrared band Cepheids. It's because, as you can see here, extinction is like very small and will affect less our results. Indeed, as I've seen, extinction is stronger going to the blue, and red and infrared are less affected. And the effect of this extinction is that the stars appear redder and fainter than they actually are, because indeed the correction for the extinction is only a subtraction of the extinction in that band. And here you can see what explained with an image that I think it's always the better way. What happens that this is the observed tip of red giant branch in LMC and SMC, and indeed this is the truest one when we take into account extinction correction. So, given an extinction law, we need to take into account what's happening to the light when it's coming, when it's traveling to us. So, to take into account this problem, astronomers at the end of last century, they introduced a new function of magnitude, that is the Wesenheit magnitude. And it's called, the definition is to be a reddening-free quantity. The only thing that we have to take into account is the extinction law. Indeed, you can see here, first of all, the reddening, I want to say the Wesenheit is defined as the difference between a magnitude in a specific filter minus the extinction law for the color into other filters. Starting from this definition of a magnitude, this is corrected for extinction, minus a color, because this is a color corrected for extinction, for the extinction law in a specific band, is equal, if you do all this calculation, is equal to say that I want to observe the magnitude without correcting for the extinction minus the extinction law multiplied for the color. And this is is an improving of the observation, a total improving. So, the period Wesenheit is not a period luminosity a period luminosity relation. It's a period luminosity color relation, but with this coefficient that allow us to do the projection in the best possible way. So this means that thanks to this projection, we have the last scatter possible. Indeed, here you can see all the relation in the HST bands. The first three, they are period luminosity relation, and you can see the dispersion. The last two relations are only period Wesenheit relation, and you can see that the dispersion, by definition, is smaller, and this means that this is a better projection of the period luminosity color plane with respect to the period luminosity relation. And it's for this reason that nowadays, in the distance ladder, the choose distance ladder, in whatever distance ladder that we use with pulsating star, we are using period Wesenheit relation and not period luminosity relation, because we found, a shortcut to have the better dispersion. Indeed, the third problem to take into account is the metallicity, because as you can see here, theory predicts that if a star enters the instability strip with a different metallicity, they will have a different luminosity. And this means that the metallicity is going to increase the dispersion of the point on the period luminosity, period Wesenheit relation. So this means that we have to take into account this to reduce the dispersion, because the thing that we want to do is to reduce the dispersion at the minimum for the period Wesenheit relation. And here you can see also observed Cepheids with metallicity measurement that we will see this evening how this can happen. And we will see that color coding is according to the different metallicity, and we can see how they spread around the relation. Because here it's corrected for everything. All the stars are at the same distance, and the only thing that is still not corrected, taken into account, is the metallicity effect. And you can see that the stars are still spread around the line. So we will see this evening. And at this point, why is also important to take into account other pulsating stars? Because thanks to the other pulsating star, we can trace systematics in the local universe. Because thanks to classical Cepheid, that as you can see here are the pink one, classical Cepheid for sure are the one that can go up to supernova 1A, because as I've told you, these are as a distance indicators. So you can see that are the ones that are more luminous and can be seen far away. Okay, but still these can be used in the local universe to search for systematic and to understand if all the pulsating stars are tracing the same distances. Just to be sure we understood these things, and precision cosmology is systematics limited. For this reason, we want to populate as much as possible the period luminosity relation, to be sure that systematics are understood. Now, since we are talking a lot about the measured distances, period luminosity relation, now let's start, let's say what are the steps that we need to do in order to actually measure the distances once we recognize a variable star. Indeed, the first thing that we have to do is to recognize this variable star, because as the first thing that I showed you was the time series-like curve that Henrietta Leavitt was just compiling for all the stars that were in the photographic plates. But then later, why she decided to take one star instead of another? Because she noticed that there was something strange in the magnitude. And since 100 years ago to now, we had two major experiments that helped us to trace the variable stars in all the galaxies. Indeed, the first one is the Ogle survey that was born with a completely different science case. They were searching for gravitational lensing experiment. But since they were scanning the sky different times, they were also collecting a lot of magnitude for the same object. And they found out that a list of variable stars. But the problem of Ogle, the limitation of Ogle is that it's in Chile. So they were scanning only the southern hemisphere. Thanks to Gaia, we also had the possibility to scan the northern hemisphere and to go far away into our galaxy, up to Milky Way, up to LMC and SMC, and so we had an enormous way catalog. And in the next years, thanks to the Rubin Observatory, we will have also the possibility to have other variable stars in more distant, like for instance Draco, other satellite galaxies of the Milky Way, because they will scan the sky, and this is more, the Rubin Observatory is more powerful of Ogle, because it's like 10 times bigger. So, okay, we see this variable star. But, why the period luminosity relation is so powerful? Because, as you, also during the talk of Lewis, have you never heard about error on period? No, never. So, this is, the relation is powerful because we can assume that the period is without error. But to do this, we have to observe the star different and several times. The more that the light curve is sampled, the better we know the period. And for this reason, Ogle, also if it's a small telescope, I think that's like a 4-meter telescope, but since they are scanning continuously the sky, they have like very small error on period, but of the order at the 10th after the 0. Probably there is an error. We will see also how this impacts the period on the light curve. And in this slide, what we are seeing is, for instance, Ogle is observing one star that is a bulge type 2 Cepheid, BL type, with period 1.6 day. First of all these, here where you see that is not observed is because of the day. Of the sunlight, and because we can observe only during the night. And you can also see that this star has a period on 1.6 day. So it's even more complicated to create a well-sampled light curve, because you have the risk, since you observe only during night and the period is almost equal to 1 day, you have the risk to observing always the same space of the light curve. So you need more and more observation. And for this reason, like for instance, Ogle was not think to do this, so it's okay. But for reason like spanning the sky and find new variable star, there are studies of when we launch a new satellite, like for instance in Gaia and new facilities, there is also study on when the telescope, and which is the velocity of the telescope that has to span the galaxy. Because related to the velocity, there is at what time are we observing a star, a region, after how much time we are coming back to that region, which kind of variables are we neglecting doing this. Because when you build a new instrument and you want to span the sky, you don't only have to think, about variables, but also about other variables, phenomena that can happen during the night. So, and this is what happens when we want to measure the period. And the period is also important because it's the period that allows us to build a light curve and to measure the mean magnitude. Because indeed, if you remember, Miss Henrietta Leavitt proposed not one, but two different period luminosity relation, because one for the maximum of the light curve that she was registering, and one for the minimum of the light curve. Indeed, today, what we use in our measurement are the mean magnitude. What does it mean? Because, first of all, what we mean when we see magnitude. As we have seen also before, the magnitude is the flux that we register at the instrument, at the telescope. But telescope can have different filters, and we also have to take into account the calibration with a standard star. And for these different zero-point flux, that the power of the choose distance ladder is that they used only one instrument, HST. So they have only to do one correction. They do the same correction, the same flux correction for all the stars that they are observing. So also if there is, for some reason, some error or something related to the magnitude, to the camera, to the standard stars that they are using, at least it's only one. You don't have to introduce one error for this instrument, another error for another filter. No, at least there is an homogeneity, and this is a powerful tool. Also for this reason, we still don't do this with a different kind of indicators, because we still don't have the homogeneity for that truth. So for sure we can do and we can check, and because since the last few years ago, they were saying, okay, I need precision cosmology to go and to have the smallest error. But now, if I take into account different ways of go to each zero, I can have different probes that, I'm tracing the right value from the early universe. We are always tracing the right value. Then, okay, precision cosmology, we need to do something more, but at least we are on the same path. And also here, another interesting thing that you can see in this plot is that different kind of star, since they have a different temperature, they emit with different black body shape. And this will be also important later this evening when we will talk about spectra. And for instance here, you can also see the filters of the HST band. That's covering all the, I think that's the visible going slowly to the infrared part of the spectrum. And also, it's also important to take to have in mind when you want to observe a star, a galaxy, something, where you want to observe that star and where the star is emitting. So you have to choose the right instrument to observe that star. And this is done thanks to the filter. So, going back to the magnitude, to the mean magnitude, in general, this is what is the shape of a type 2 Cepheid after several observations, and the mean magnitude is the area that is down this shape. And you have to measure this. At this point, you have all the three, you have the two things that you need, the period and the mean magnitude. And for instance, you can just plot a period Wesenheit relation. This is a period luminosity relation in K band, and is corrected for extinction. And this is for type 2 Cepheids, for all the type 2 Cepheids. Indeed, here you also have the Arwood Tauri. In red, you have the Arwood Tauri. But the one that we use for purpose of the distance ladder are only the blue and the gray. That you can see, I've done this plot, and there is no artificial, the only thing that we took was were the magnitude from the Vista telescope in the JK band, the correction for the extinction, and you can see a line, that's there. Then the thing that you do to know these two coefficients, alpha and beta, is a linear fit. And also, for this reason, it's powerful, the period luminosity, because it's a linear relation. You have to do a linear fit, and you retrieve alpha and beta. Indeed, you can also do the same for this is a period Wesenheit relation, where you only have to calculate this coefficient according to a specific extinction law, and then it's done. Here you don't have to know the extinction measured in the Large Magellanic Cloud. You only have to know the extinction law. That's the extinction law. We use the extinction law of the Milky Way because the light is traveling into the Milky Way to us. At this point, the second step is the calibration with the Gaia parallaxes. How this is possible? We need to, for every single Milky Way Cepheid, we have the Gaia parallaxes, we have multiband photometry, we have also a beta, that is the slope, because we can retrieve the slope from another galaxies, and we are missing alpha 0. But if we want to use the method of the photometric parallaxes, what happens is that we have the photometric, we have the Gaia parallaxes, and we can calculate a photometric parallaxes that is linked to the observable quantities, because indeed this is the Wesenheit in the Gaia band that we know only if we know the magnitude in the Gaia band, we can retrieve this number, and this is the period. So what we do is a chi-square minimization, and we can obtain the alpha and beta of the Milky Way. And we will also see this evening in the exercise how can we just numerically do this. At this point, we know alpha Milky Way, so this means that at this point we know the absolute alpha that's coming from the Milky Way, because this is coming from the Gaia parallaxes, and this is absolute, is not relative. And what we do is simply this. It is a difference between the observed and the absolute magnitude, because this is the observed magnitude of a Cepheid, and this is the absolute magnitude if the Cepheids would be in the Milky Way. At this point, what we retrieve is the distance for every Milky Way. We retrieve a number. If we do an histogram of this number, we can say that the mean value is the distance of LMC. Like for instance, from these are type 2 Cepheids, the distance that's coming is 18.456, and the distance that Louis explained this morning done with the eclipsing binaries is 18.477 plus 0.3. And this is using Gaia parallaxes, Gaia data, and period from Mogle. A way in which we can use the population to distance indicators is calibrating the tip of red giant branch. Indeed, what you can do is to calibrate the distance of the globular cluster, because in the Milky Way what you do to have a tip of red giant branch that I think Sean will explain tomorrow is that you have to have also in this case, the problem is always the calibration, you want to build a color magnitude diagram in absolute term. So you can use the distance given by population to distance indicators in the galactic globular cluster to calibrate the color magnitude diagram of the Milky Way. And you can obtain an estimate of the tip of red giant branch. Then you can use this estimate to retrieve a value of each node. And this is what we can do at the moment. Now, what I want to just give you this overview, which is the workflow that you have to do when you observe a variable star to obtain a distance. Just to repeat, you have to find a variable star. You can find this repeating observation. Then you need to fit a light curve to obtain the period. Then the period determination, you can also fit the shape of the light curve. Then you can have a mean magnitude. Then you can observe the star in a plane that is or a period luminosity or a period Wesenheit plane. You can fit another time the linear relation between period and magnitude. And at this point, you can anchor them with the Gaia, parallaxes, with maser, with eclipsing binaries, you have the 0-point calibration, and then you can go further away. So, my take-home message that the first step of our lesson was the discovery of the role of the Leavitt law, because as we see this morning, the Leavitt law was the law able to close the great debate. Otherwise, we will not know that there is something outside the Milky Way. I want to remember you the period luminosity color and its limitation. And as you can see here, the limitation is that we have to do a projection of this relation on another over the plane of the period and luminosity. And I want to remember that we still have one open point, that is the metallicity. What we also have seen this morning in this lesson is the physics of a pulsating star that is well understood. That the pulsation is something that the change in opacity of the external layer allow the star to contain, to be in heat engine and to store energy during the compression and then to have more luminosity in the expansion. Then we have seen how to measure distances with pulsating star. And I want to just to underline that the power of pulsating stars that are not only distance indicators, but indeed they can also be used as probe of stellar physics, because when we study a spectra of a star, we can know about the atmosphere and the elements that are present in the atmosphere. And this evening we will see this. And it's to know the elements that are present in the atmosphere of the star. It's not only useful because, okay, we know the metallicity, the iron of the star, but it's because we know all the elements that are present, and this gives us information about the molecular cloud from which the star was formed. Standard candles, pulsating star can help us also in stellar evolution and population, because as we have seen, stars can cross the stability strip coming from different evolutionary paths. So if we know that in some globular cluster, some open cluster, there is a Cepheid, there is another light, this means that there are old stars, there are young stars, where these stars are coming. Galactic archaeology, because for instance, thanks to Gaia, we found out that the Milky Way in the past century was not only the Milky Way, but it's made up of 7 different galaxies, and the pulsating star can trace the different galaxies. Then this can be used also to calibrate other astrophysical quantities, like for interferometry and astroseismology. And in the future, as I've told you, the time domain era, when we will have a lot of instrumentation and we can observe in different ways the pulsating star, more distance that we are observing now. So, I want to leave you with this nice look at this. This was about the first light of LSST. And these are just 2 days of observations and of that analysis with LSST. You can see how much is powerful and what is waiting for us. So this was my last slide. And thank you for your attention.